Alright guys, hopefully this video is going to give you a quick tutorial on how to solve what in chemistry is called a basic calorimetry problem. We just need to be able to solve the basics of it, and let's go over what we're talking about. The problem that I'm referring to in our thermodynamics packet is the problem that starts on 18. It's about dropping a hot piece of aluminum into water, and we expect, of course, the hot aluminum will cool down and then the relatively cool water will warm up. So the concept that we're thinking about is a concept of heat transfer. And the expression for heat transfer, heat is Q. We can talk about the heat contained in an object or its ability to transfer heat based on the mass of the object, that's M, the specific heat capacity of the object or the material, and then the change in temperature, right? And then remember, change in temperature, delta, it could always be expanded as final minus initial. The physics of this, or the chemistry of this, is that we're going to put in a piece of hot metal. It's going to cool down, so it's going to lose heat. So it should be a negative value that we're going to lose heat with. And then that heat's got to go somewhere. First law of thermodynamics says that we can't gain or lose heat, but it can be transferred. So it's going to be gained by the water. So the water will have a positive value for Q. So we just take our expression for Q and we expand it out. So this will be what I'm thinking about for the aluminum, and it'll be negative. And this will be what I'm thinking about for the water, and it's going to be positive. So what do we know from the problem? We know that we're dealing with a 1 kilogram mass of aluminum. The specific heat capacity for aluminum is 900 joules per kilogram per degree Celsius. You never have to memorize that. It was given in our notes, but you could always look that up in a table or online for heat capacities. And then delta T, well, we don't know TF. That's what we want. But we know that that aluminum was 90 degrees Celsius before it went into the water, so its initial temperature was 90 degrees Celsius. For the water, we're dealing with a larger mass, 4 kilograms. Heat capacity of water is pretty large, 4,184 joules per kilogram per degree Celsius. And again, TF we don't know, but we do know TFs will be the same value because they're going to come to thermal equilibrium. But the water starts off at 25 degrees Celsius, right? So the following is just algebra. Once I've understand the concept and the physics of it, the rest of it is some algebra. I left the units off while I'm doing the algebra just so it's a little bit cleaner. But this is what I did, is I just multiplied these numbers together. So 1 times 900, I got negative 900 times TF, 900 times 90, that's how I got that. This side I multiplied 4 times 4,184, got that, and then multiplied it by the TF. And then these three numbers multiplied, so we get that value. Now, what we want is we want to isolate TF. So my tactic was to add 900 TF to both sides. So I get 900 TF minus 900 TF. It disappears from this side, but it's added to this side, right? Algebraically, then I want to also then add this constant to both sides. So if I add positive 4,400, 18,400 here, on this side it disappears, but I got to add it to that side also to maintain the equality. And this is what it distills to. And I think at this point, if I just showed you this, everyone would be able to solve it, right? It's the algebra of getting there, but I want to solve for TF. Right? So TF, I just factored out and got this value, and then I take these values, divide them, and then what my final answer is 28.3 degrees Celsius. And that should make sense. We should check our answers, right? What does that mean? It means, well, the aluminum went from 90 to 28.3. That makes sense. It's supposed to cool down. And the water went from 25 to 28.3. So that makes sense. That should cool down too. I mean, that should warm up.